Okay, so in this question, we are presented with this graph here. Let's check out the axis. So the vertical axis is actually the electric potential energy stored in the pair of ions. So it's actually the electric potential energy, which is a form of energy, of course. So this graph is showing the variation of a form of energy with distance. So you must know this relationship, that the field force is equals to negative du dr. This is the general equation. So for our situation here, we are actually talking about the electric force being equals to the negative of the gradient of EPE with respect to distance r. This equation is actually presented as F goes to G in this question. In fact, we are asked to explain how this relationship come about. So to do that, it has got to do with work done being equals to force applied through a distance. And for our situation, it's about the increase in electric potential energy comes about when we do work against the electric force through a distance. I repeat, to gain electric potential energy, we have to do work against the electric force through a distance. If you rearrange this equation, you get this relationship here. So what does this relationship tell us? Two things. First is magnitude, second is direction. So this tells us that the magnitude of the electric force is strong when the gradient is steep. So you're going to have a very strong force here because the gradient is very steep here, but not a very strong force here. You get a force here also, but definitely not as strong as, say, here, because the gradient is steeper here. Second, the direction. So this formula tells us that the direction of the electric force is always opposite to the gradient. Or another way to put it is the direction of the electric force is always opposite to the direction in which the EPE is increasing. Alright, so let's look at here. Is there a direction to the electric force here? No, because the gradient here is 0. The magnitude is also 0. There's no direction about it. Electric force is 0 at this point. But anywhere beyond this point, you have a positive gradient. If the gradient is positive, it means the electric force is negative. That means the electric force is directed towards the left. Alright, any point that is closer than this point here, you get a negative gradient. If the gradient is negative, then the electric force is positive. Positive means towards the right. The other way of figuring out the direction is also very easy. Just ask yourself, when you're here, the EPE increases towards the right, right? So if the EPE increases towards the right, the electric force must be towards the left. A point here, if we are here, then the EPE increases towards the left. If the EPE increases towards the left, it means the electric force must be towards the right. Okay, so basically the situation looks like this. If the ions are separated by this distance, it experiences a 0 electric force. That's why this is the equilibrium position. If you are further than this, if the separation is too big, then you experience an electric force that tries to reduce your separation. That's why this is an attractive force, because you are trying to pull the two ions closer together. On the other hand, if the two ions are too close together, that means to the left of this equilibrium position, then they experience an electric force that try to increase the separation between them. That's why this is a repulsive force. So you experience zero force at the equilibrium position. Too near, you get repulsive force. Too far, you get an attractive force. That's why in the subsequent part of the question, you'll be you'll be talking about oscillation, about the equilibrium position. Okay, that's all I have to say for this part. Ta-ta!